There are so many good problems to solve related to forces. Let's do a fun one here. So we have a system of two blocks, one on top of the other. They're sitting on top of each other and connected together via pulley, these two strings, and big M and little m. The coefficient of friction is the same on all the surfaces. We're going to figure out the acceleration in terms of the given quantities. And you could probably look at this and say, all right, big M here is going to win. So it's going to accelerate down, which is what it wants to do. But because this is a string that's connecting these two, it's going to force little m to accelerate. So those are the accelerations. Well, let's do a free body on both of these masses. You really need to do that because we need to account for all the forces or we're going to get ourselves messed up. So first, free body on little m. So the coordinate system I'm going to choose is a logical one. X in the direction of the ramp, y perpendicular. Let's put the block there. mg acting down, angle phi with respect to y. And then tension is acting on that block upward. The normal force. And now, what about the friction force? Since this block is accelerating upward, it's sliding along this block. So this block is applying a force to the small block that's acting downward. So first let's resolve mg into its mg cosine of phi perpendicular component and the parallel component mg sine of phi. And then let's add the friction. So there's our free body diagram. And the friction is mu k normal, which is mu k. The normal for the small block is just mg cosine of phi. So we can now write the sum of F in the x direction, ma, and that's sum of the forces is the force that wins, which is the tension acting on the block, minus the forces detracting from that, mg sine of phi, minus the friction force, mu k mg cosine of phi, which is ma. And there is an expression for the sum of the forces acting on the small block. Now let's consider the forces acting on the large block. Let's do a free body, choosing a coordinate system that's logical. So first of all, we have mg acting straight down at angle phi with respect to y, perpendicular to the ramp here. We have our normal force. We have tension acting on block M directly. Let's resolve the weight into its perpendicular and parallel components. Now, we also have forces from the little block on the big block. Right? So this thing is not in isolation. It's got this little block pressing into it, and it's also got the little block sliding on it. So that has to be taken into account. So let's put the normal force. That's mg cosine of phi. That's pressing into the block. So this should be the correct direction for that force. We also have the friction force of the little block on the big block. The little block is sliding up. It's trying to drag this large block up the ramp. So the friction force, this sliding up against the block, does not mean the force goes in the opposite direction. It's actually in the same direction that this block is sliding. Or you could think the large block is sliding down. It's sliding underneath the little block, and therefore the friction is in the opposite direction of that, which is up. Or just think of the little block sliding against the big block, trying to drag it up the ramp. Does that make sense? In any case, that force is directed upward. And it's mu k mg cosine of phi, just like we already determined. But in addition to that now, this big block is sliding down, so it has a friction force against the ramp itself. And of course, opposite the direction of motion, which is down. So the opposite direction is up. So it's also in the same direction of the friction of the little block on the big block. So there it is. And the other thing to keep in mind is that friction is, of course, mu k normal. And the normal force acting on this big block is affected by the mass of the little block pressing into this big block. Lot to keep straight. So this normal force has to be carefully considered. The sum of the forces in the y direction is equal to 0. So the sum of those forces will dictate what the normal force is right here. It's the perpendicular component of big M plus little m added together. So here's the normal force. The normal force is the combination of little m plus big M times g cosine of phi. So you're adding the contributions of gravity acting on both of those blocks. So there's our rather complex normal force. Now, sum of Fx equals ma. We can go ahead and write the equation. We have the winning force, mg sine of phi. That force wins, even though it doesn't maybe look like it here. I don't have these vectors drawn to scale. But it wins out over everything else. So everything else is subtracting. So we have tension pulling against it. We have mu k times normal, which is m plus m cosine g cosine of phi. So that force of friction and the force of friction from the little block, mu k little mg cosine of phi, equals ma. We can simplify that a little bit. Mg sine of phi minus t minus mu k. Well, we have a little m here, we have a little m here, times g cosine of phi in both cases. So we can bring that together as 2 little m plus big M g cosine of phi. And that's ma. So there's our expression that emerges from the big block. So now we have 2 independent equations that we just solved. If you need to, go back and go through again how we did that, if necessary, of course. So we have these 2 expressions, and you'll notice that there's a t here and a minus t here. It kind of is begging to be added together. They are begging to be added, and we'll eliminate t when we do that. So let's do it. So we have mg sine of phi. There it is. We have mu k 2m plus m g cosine of phi. We're going to subtract mg sine of phi and mu k mg cosine of phi. And that's m plus ma. Now we have m minus m g sine of phi, so that takes care of these 2 expressions. These 2 terms, I should say. And then we have minus mu k. This term and this term both have mg. Well, they have g cosine of phi. There's 2m there, which with a minus. There's another minus 1m here with mu k, so that's minus 3 of these, which can be written this way, eliminating those 2 terms. Minus mu k 3m plus 1 big M g cosine of phi is m plus ma. And so finally we can write the expression for acceleration. Isn't that awesome? Isn't that satisfying? There's the acceleration of this marvelous system. I hope you're impressed. Hold on, we're not done with this problem yet. We still have to figure out what minimum angle is required for the acceleration to be there, to be non-zero. Obviously, if it's sitting flat, it's not going to accelerate. As you can imagine, lifting one side, as the angle increases, the forces increase to the point where it eventually will start to accelerate. So what is that minimum angle? Well, here's our expression for acceleration. And for this to be greater than 0, of course, the numerator has to exceed 0. So let's just write that down. This is pretty easy to manipulate, and we see that the left side has to be greater than the right side. So what it looks like it's trying to do is first of all have g go away. So let's make g go away. And then we see a sine of phi and cosine of phi on the other side. So we can divide those. Sine of phi over cosine of phi is the ratio of what's left. Mu k 3m plus m, big M, divided by big M minus little m, which of course is tangent of phi. And this is the requirement on the angle so that it actually accelerates. How beautiful. Let's finish this little lesson up with an example. We have a curve that's banked for 15 meters per second to be the just right speed, and it's got a 120 meter radius. Now the car is going to go around this curve at 30 meters per second. Way too fast, right? So it's going to need friction to keep it from sliding off the outside edge of the road as it goes around the corner. This is a cross section. So what minimum coefficient is going to be needed? Well, the first thing we need to do is figure out what this angle is in the first place. If it's just right for 15 meters per second, we better figure out what phi is. So let's do that. So we got weight, we got normal, and there's that angle with respect to the vertical. So we have normal cosine of phi, normal sine of phi, breaking the normal into its components. And of course, normal sine of phi is going to be the centripetal force. So the ideal speed, we have normal sine of phi is centripetal force mv squared over r, and the vertical component of the normal exactly cancels mg, the weight, so that it doesn't accelerate vertically. So normal cosine of phi is mg. These want to be divided, so let's divide them. And sine of phi over n cosine of phi is tangent of phi, and that's the ratio of these two expressions where m goes away. We get v squared over rg. So now let's solve for the angle. Inverse tangent of v, 15 squared over 120 times 9.8. We get 10.8 degrees. The just right angle for this, for a 15 meter per second vehicle. But we've got it moving at 30 meters per second. So now we got to add in here how much friction we need to execute this corner. Now let's redraw this problem considering the actual situation of the car moving at 30 meters per second. So we got mg, we got the normal. Normal's pretty big. Phi with respect to the vertical, same as the ramp angle. Break it into its components, that normal force. We have normal sine of phi and normal cosine of phi. Wiggle out the normal. Recognize that this vertical component of the normal force is bigger than mg because we have not added friction. But we have friction acting down the ramp, which is necessary to keep the car from flying off the outer edge of the road. That friction is mu normal, and based on the direction it's going, we know that the horizontal component is going to be related to the actual force times the cosine of the angle. So there it is, mu s normal, cosine of phi. And the vertical part, which is a real force, mu s normal sine of phi, gets added on, and then we wiggle out the friction force. So there we have it broken into its components. And now, keeping the big picture in mind that mu s is friction over normal force. What is the minimum coefficient of friction needed for this problem? Sum of the forces in the x, normal sine of phi, right there, this green one here. If you hear noises in the background, don't worry, it's just my wife making granola, and as soon as I'm done with this recording, I'm going to get me some of that granola, then I'm going to go out and chop some wood after that, so I'm looking forward to it. So if I start talking faster, you'll know why. All right, and added to normal sine of phi, we have mu s normal cosine of phi. That's the part of friction that's contributing to sum of forces in the x, which when added together gives us the centripetal force mv squared over r. Let's solve for mu s from this expression. So here it is. mv squared over r minus normal sine of phi all over normal cosine of phi. Let's now write the sum of the forces in the y, which of course is going to be this minus all this, which have to add up to 0. So normal cosine of phi minus mg minus mu s normal sine of phi equals 0. And we see the normal in two places here, so let's factor that out. Normal cosine of phi minus mu s sine of phi equals mg. And now we have a couple of expressions. We have mu s, we have sum of forces in the y, gives us an expression for mg, so let's put this all together. So now here's our two equations. our equation for mu s that we already solved. And then when we did sum of the forces in the y, we had an expression, and we can solve that for normal. And we get this expression here. Well, what are we going to do with this? We have an expression for normal. That's nice. We could sub it in every time we see normal, but unfortunately, we see the mu s in there, and that's what we're trying to solve for. So this is going to get a little messy, isn't it? What should we do? Yeah, okay, let's brute force it. I don't know what else to do with it. So I'm going to look at n sine of phi plus mu s normal cosine of phi. So I brought this up here and brought this over here. So those two terms are on the left side, and that's mv squared over r. Okay, that's nice. On the other side, this thing, let's do n cosine of phi minus mu s normal sine of phi equals mg. So that falls out pretty nice. Well, let's divide these two. And if we do that, the normal will go away because it's in every term. And over here, the masses will go away. So that'll help us a little bit. Yeah, there it is. A little bit simpler now. Now this is 4v0 squared rg if you consider that v0 is our just right speed that we determined before, because the v that we're actually talking about is twice that speed. So 2v0 quantity squared is 4v0 squared, where v0 is the just right speed. But if you take v0 squared over rg, remember what that is. That's actually that just right speed consideration, which is tangent of phi. So this whole thing is 4 tangent of phi. All right. Having gotten this far, we can now do some more algebra. So multiply this by this part, 4 tangent of phi cosine of phi minus mu s sine of phi. There's mu s sine of phi times 4 tangent of phi. So basically multiplying the bottom part by 4 tangent of phi equals the top part. There it is. Now, this matched up with this, we have, I'm going to bring this over to the other side, essentially, changing the sign. 4 mu s tangent of phi sine of phi plus mu s cosine of phi equals this minus this term, which I'm bringing over. So 4 tangent of phi cosine of phi minus sine of phi. So I think I got everything right so far. I suppose we should just leave it alone at this point, but as long as we've come this far, let's see if we can finish it up. All right, so if I didn't say it before, the reason I set the expression up like this is to get all the mu s's on one side, because that's what we're trying to solve for. So now we can factor it out. There's mu s factored out. And now we can solve for mu s minimum by just dividing. So we have these two terms divided by this term. And that is mu s minimum. So we can plug in the particular angle. So it's 10.8 degrees. So every time phi shows up, we'll plug that in. And hopefully we can put that into the calculator correctly and come out with the correct result. When I do that, I get mu s minimum is equal to 0.5. But I have done that actually several times, and I think this is the correct expression. But I would be very happy for you to verify it and make sure that that's actually true. But hopefully you were able to follow through the process of analysis to get us to this final solution, to the minimum coefficient of friction needed to execute this corner. And 0.5 is not asking too much. Most roads will give you a coefficient of friction of 0.5 without too much trouble.